Hello everyone. So today we are going to be doing word problems that use the fundamental theorem of calculus. So we're just going to go through and do like 6 or 7 of these. This is a homework that is due, I believe, tomorrow night on WebAssign. So this would just be a good video to watch. So let's just begin. So water leaks from a tank at a rate of 2 plus 5t liters per hour, where t is the number of hours after 7 a.m. How much water is lost between 9 and 11 a.m.? And so the thing you need to notice is that this is a rate. So this is our derivative. And so we got a rate of change, and we want to know how much is lost. So this is a total change. So this is a hint that we're going to need to set up a definite integral. And so we're going to have a definite integral, and we want to take the definite integral of the rate. And then the only thing we need to figure out is what are our limits of integration. And so here we're starting at 9. Actually, what you first want to notice is what's your variable? T, it's time. And so if this is time, then the things that are limits of integration will be times. So from 9 to 11. So you might be tempted to write 9 and 11 as your limits of integration. But t is the number of hours after 7 a.m. So instead of 9 and 11, we would instead do 9 is 2 hours after 11, and 11 is 4 hours after 7. So our limits of integration are 2 and 4. So we integrate this, so it's going to be 2t plus 5 halves t squared when we take the integral, our antiderivative, from 2 to 4, which is equal to 2 times 4 plus 5 halves, 4 squared, minus 2 times 2 plus 5 halves times 2 squared, which is equal to 34 if I did my arithmetic right. I might be doing my arithmetic wrong, but anyway, we just go through and we solve this. So this problem was pretty straightforward. Let's go and look at something a little different. So now we're going to look at this problem. So the number of cars per hour passing an observation point along a highway is called the traffic flow rate, Q of t, in cars per hour. So Q of t is how many cars is passing a certain point along a highway per hour at any given time. And so which quantity is represented by the integral from t1 to t2 of Q of t dt? So looking at this, we have T1 and T2 are your starting times and your ending times. Q of t is your rate, and dt is just telling you that your time is the thing that you're adjusting or going through. And so this is going to be a total change because it is a integral. So it is a total change. A total change of what? Since QT is cars per hour, it's a total change in number of cars passing a certain point on the highway between time t1 and time t2. Okay, so we know that it's a total change. You look at what the rate is of. So it's cars per hour. So that's a hint that it's a total change in the number of cars. And then I just gave a little bit more context in terms of the problem, and then remembered to mention these limits of integration. All right, let's look at this next one. So the flow rate is recorded at 15-minute intervals between 7 and 8 a.m. Estimate the number of cars using the highway during this 2-hour period. So there are really 2 choices. We could either estimate with a left sum or with a right sum. So if we break this up in the first 15 minutes, So this is first 15. This is the second 15. This is the third 15, and here's the fourth 15. And for each 15-minute interval, you can either pick the first rate or you can pick the second rate. And so it doesn't really matter, but if you notice, it's mostly increasing. So if we pick the second rate of each 15-minute interval, we're probably going to get an overestimate. It's not always true. At 8, we now go down again, but for all the other intervals, it is an overestimate. And so I'm going to do a left sum just because it doesn't really matter. You could choose to do a right sum. And so for 15 minutes, remember this is cars per hour. So instead of multiplying by 15 minutes, we want to multiply by a quarter of an hour, right? And so if we're looking at that first 15 minutes, then we're going to have a quarter of an hour times 1,044 cars per hour. So that's that first 15 minutes. Right here, we have the choice. And then the second 15 minutes, it's still going to be a quarter of an hour now times the rate of 1297 cars per hour. And then the third 15 minutes is a quarter of an hour times a rate of 1478 cars per hour. And then the last 15 minutes, you still have a quarter of an hour times a rate of 1,844 cars per hour. And we stop. You don't use the 1451. Because then what you're saying is that there's another 15 minutes, another quarter of an hour that you're going to keep track of, but there's not. So you could have picked the right sum and started with this term, and then you'd add one more. But you cannot do 5 terms if there's only 4 sets of 15 minutes. Okay. And we get, that's trying to draw with the pointer. And you get 1,415.75 cars. All right, just want to make a note here. I've had a lot of students say, wouldn't you write 1,416 or 1,415 cars? Yeah. I see no problem in doing decimals for this. Like, you might have a car that's only partially past that point on the highway. So whatever you want to do for that is fine with me. So let's go and do a couple more problems. All right. So let's look at this guy. A particle has a velocity of v of t equals t cubed minus 10t squared plus 24t meters per second. Compute the displacement on the interval 0 to 6 and the total distance traveled over 0 to 6. So there is a difference here between displacement and total distance traveled. All right, so velocity you can think of as distance over time, right? All right. But in fact, it's distance over time. But distance, oh no. No, I was right. Ignore my oh no. It's distance over time. So what's the difference between displacement and total distance? So I'm going to draw a picture real quick and then I'm going to erase it. So let's say that I go on a walk and I walk this way and then I turn around and I walk back. So total distance is going to be this and this together, right? This and this together. Displacement is going to be the difference between the starting point and the ending point. So total distance is everything together. Displacement is the difference between the starting point and the ending point. Okay, does that make sense? All right, so let's go through and let's solve this. So one of these guys is going to be just straight up the integral. of t cubed minus 10t squared plus 24t dt from 0 to 6. And then one of them is we're going to be counting everything as positive. Okay, so this is displacement. Because this is a total change. And the total change does not care if you had some increases in the middle there, some decreases in the middle. It's just like, what is the difference between the beginning point and the ending point, which was the definition of displacement. And so we go through and we take our antiderivatives. So that's t to the 4th over 4 minus, let me erase that. So minus 10 over 3 t cubed plus 12t squared from 0 to 6, which is equal to 6 to the 4th over 4 minus 10 thirds 6 cubed plus 12 times 6 squared, which is 36 meters. All right? Okay. So this is our displacement. It's 36 meters. If you notice, I didn't plug in 0, so really what I should have done is minus and then plugging in 0. But whenever you plug in 0 for t, you're just minusing 0. So always pay attention, see if that always works. It doesn't. Sometimes you end up with an antiderivative where plugging in 0 is not 0. Think trig functions. But in this case, it is. And so we get that the total displacement is 36 meters. So then we want to figure out how are we going to do distance. So in order to do distance, we're going to want to find when we're moving forward. Forward. I am not spelling that correctly. So when we move forward and when we move backwards. And we want to make them both positive. But forwards, v of t is positive, and backwards, v of t is negative. So we need to find where the velocity is negative. So let's start by setting it equal to 0 and just seeing where it changes. So 0 is equal to t cubed minus 10t squared plus 24t. And then pull out a t, and you end up with t squared, 2. It's t squared minus 10t plus 24. And then this should factor into something nice. So it's 0 equals t times t minus 4 times t minus 6, because negative 4 times negative 6 is positive 24. So we get that the three places where we potentially change direction is at t equals 0, t equals 4, and t equals 6. Of those, our ending points are 0 and 6. So we don't really care about these two places where it changes. We do care about what's happening at 4. So 4 is where we're going to want to split our integral. But first, let's just check where it's positive and where it's negative. So before 4, so let's check at 1. So the velocity at 1, and let's check after 4, so the velocity at 5. So v of 1 is 15, and v of 5 is negative 5. So that means from 0 to 4, we have a positive change, and from 4 to 6, we have a negative change. So we're going to split this up into our integrals. So from 0 to 4, plus our integral from 4 to 6. From 0 to 4, it's positive, so it's going to be the same as before. We've got that t cubed minus 10t squared plus 24t dt. Gives us our first bit. And then from 4 to 6, since it's a negative direction, we want to make that negative distance into a positive distance. And so I know many of you would be tempted to use like absolute value, but in practice, you would just take the negative of the negative. So it's negative t cubed minus 10t squared plus 24t dt, which then you can pull that negative sign oops, and then we can pull that out in front. And so we can turn that plus into a minus. This will just turn this whole piece into a positive value, because you want to remember, for distance or total distance traveled, you want to do this distance plus this distance. Even though it's a negative velocity, we want to add a positive distance here. So you would go through similarly as before. You would take the antiderivative of both of these. And so you end up with t to the 4th over 4 minus 10 thirds t cubed plus 12t squared from 0 to 4 minus the whole of that t to the 4th over 4 minus 10 over 3 t cubed plus 12t squared from 4 to 6. Okay? So, when you solve this, plugging in these values, you should end up with, so plugging in 4 into this, you get 42 and 2/3, which I'm just writing as 42 plus 2/3 so I don't confuse myself. And ultimately, if you notice, you get a minus minus, so they don't cancel exactly. So you get that negative 36. 49 and a third. Which is approximately 49.33. And if I wanted to, I could go find into the mixed fraction, but I don't want to. So that is the total distance traveled. So notice that there's a difference between the displacement and the distance. So the displacement is 36, and the distance is 49.33. So yeah, kind of cool that those are different. All right, let's go on and do a different problem. So a marginal cost, or the marginal cost of producing X computer chips in units of 1,000 is C prime of X is equal to 300X squared minus 4,000X plus $40,000 per 1,000 chips. So find the cost of increasing production from 10,000 to 15,000 chips. And so we are given a rate of cost of producing, so that marginal cost, and we want to find a total change in cost. So we're going to do an integral, and we're going from 10,000 to 15,000, but remember X is in units of 1,000, so it should be from 10 to 15 of this 300X squared minus 4,000X plus 40,000 dx. And so to solve that, we find the antiderivative, so that's going to be 100x cubed minus 2,000x squared plus 40,000x from 10 to 15, which gives us, when you plug in 15, you should get 487,500 minus, and then when you plug in 10, you get 300,000. Okay, and I'm using the table function of my calculator, my TI-83 or 84, in order to find these values quickly. And this gives us $187,500 is our total cost of increasing production, our change in cost. So determine the total cost of producing 15,000 chips, assuming that it costs 30,000 to set up the manufacturing run. And so we want to find that total change in cost up to 15,000. So that's going to be from 0 to 15 of that 300x squared minus 4,000x plus 40,000 dx. And then when we find that total change, you want to add the 30,000. You just want to add that 30,000 because this is going to give us the total change in cost from 0 to 15. But it's not going to include that initial cost. So you need to include that initial cost yourself. So going back, You end up with the antiderivative is 100x cubed minus 2,000 x squared plus 40,000 x. And you're going from 0 to 15, and then eventually you add the 30,000 in, which is going to be equal to that 487,500, boop, 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 minus, and then when you plug in 0, you get 0, plus 30,000 for that initial cost, which means the total cost is going to be $517,500, I believe. Let's do one more type of problem. All right, Mr. Donahue has taught kindergarten for 2 decades. He has noticed that throughout a school year, he goes through glue at a rate of G of T is equal to 0.7 sine of 0.9 T plus 0.7 cups of glue per day, where T is the number of days since the start of school. Find a function that gives the amount of glue his students have gone through since winter break, 145 days into the school year. So this one is a step up in how many things you have to keep track of. So first off, we have a rate, this G of T, and it's cups of glue per day. All right. And then we're asked to find a function. So if we're asked to find a function, we're not going to get a number as our answer. And in fact, we're going to get a function as our answer. So that's a hint that this is a fundamental theorem of calculus part 2 word problem, because you get those accumulation functions from part 2. And so if we set this up, since it's a part 2, we're going to end with x. And we're going to be doing it with this rate, so 0.7 sine of 0.9 t plus 0.7 dt. Okay? So then what you want to know is, like, where are you starting keeping track of the amount of glue? And so find a function that gives the amount of glue students have gone through since winter break, 145 days into the school year. So I think maybe the words that should appear, which is. The winter break is 145 days into the school year. So you start keeping track at 145. And so this is what we want to solve. This is what we want to solve. And so we're going to take the antiderivative. So the antiderivative of 0.7 sine of 0.9 t is going to be 0.7 over 0.9. Antiderivative of sine is negative cosine of 0.9 t plus 0.7 t. Okay? And this is going to be from 145 to x, which is equal to negative 0.7 over 0.9 cosine of 0.9x plus 0.7x minus negative 0.7 over 0.9 cosine of 0.9 times 145 plus 0.7 times 145. Okay, so if you notice, we ended up with a function. We have x's here, and we will have numbers. And so to clean this up, you would end up with negative 7/9 cosine of 0.9x plus 0.7x minus 101.4. And this is an approximate amount, the 101.4. But yeah, that will be a function that gives the amount of glue his students have gone through since winter break. And so this is a fundamental theorem of calculus part 2. All right. For next time, I want you guys to go through, and I want this to be your you-do problem. Okay, so a population of insects increases at a rate of 200 plus 10t plus 0.25 t squared insects per day, t in days. Find the insect population after 3 days, assuming that there are 35 insects at t equals 0. And then I'm going to go through and do, today's Monday. I'm going to do Fridays, you do. So these are just the fundamental theorem of calculus, part 2. And so the derivative of the antiderivative of sine cubed t dt, and since we're starting at pi and going to x, is just going to be sine cubed x. That's it. Whenever you just have a number and a plain x on the top, then you don't have to worry about anything. Now, this second one is a little bit more involved. And so I'm going to call sine cubed t f prime of t. All right? So then, when you take the antiderivative of this guy, then you are going to have f of t from 3 root x to pi. Okay? Which is equal to the derivative of f of pi minus f of 3 root x, and then f of pi is a number. F of pi is a number, so when you take the derivative of a number, you end up with 0 minus, and then we have f of 3 root x. Now, 3 root x is a function, so you have a function inside of another function, so you need to use the chain rule. So I'm just going to rewrite this as 3x to the 1/2. And when we do that, it's going to be the derivative of the outside, so that's f prime, leaving the inside the same, so that's 3 root x, times the derivative of the inside. And the derivative of the inside is going to be 3/2 x to the negative 1/2. And so this cleans up to be minus f prime of 3 root x, all times 3/2, and then x to the negative 1/2 is root x under the division symbol. And then our f prime, remember, is that sine cubed. So it's sine cubed of 3 root x, well, minus sine cubed of 3 root x times 3 over 2 root x. Okay, so it's a little bit more involved than the previous one. But that was Friday's You Do. Today, I will not have my normal Zoom 30 minutes. I should have it on Wednesday and Thursday, but I am going to be traveling this week in order to take care of some important things. So if you need to contact me and ask questions, it might be a little bit touch and go in the next few days, but please try. But otherwise, have a great rest of your Monday.